This whiteboard tutorial is going to go through the oxygen hemoglobin dissociation or saturation curve. So we're going to be zooming in and out of here, so bear with me as we kind of zoom in to look at our little red blood cells. So before we get into our saturation, we have to understand what's going on with this red blood cell. So remember that our typical red blood cell biconcave disc has no nucleus, which is and can cause problems. So the question is, how does it do work? How does it get energy? So we're going to talk about it first and foremost as being a sack of protein. And we say, okay, well, what's that protein? We talk about hemoglobin, right? And we'll say that we have hemoglobin as a protein filling this sac, and we say, well, how much hemoglobin? And we tend to say that 4 oxygens bind to every hemoglobin, and people just make that direct assumption that every red blood cell has 1 hemoglobin that binds 4 oxygen and we're good to go. When in actuality, we get per red blood cell roughly 270 million hemoglobin molecules within each red blood cell. Again, that's an average. So then we go to our red blood cell and say, well, how does this thing do work? Well, how does it get energy? Well, we work through the process of glycolysis, okay? Glycolysis. And what this pretty much does is it takes glucose and it's going to convert it to pyruvate. And what this is going to do is it's going to give us the ATP we need in order for this cell to do work. Now, we're going to come back to this a little later because there is a byproduct of this right here that we are going to have to talk about that does affect the oxygen saturation. Our next step in this process is to look at actual hemoglobin. If we go back to our red blood cell that we talked about back when we did blood, we remember that hemoglobin has 4 subunits, an alpha 1, an alpha 2, a beta 1, and a beta 2. So we're not going to get too crazy with that right now, but we do want to talk about how oxygen is going to bind to this hemoglobin. So we have an oxygen molecule that comes in, and it's going to bind to our first hemoglobin. And what this does is it's going to cause an increase. So we're going to change this to red, and we're going to cause an increase in the affinity of oxygen to its neighboring subunit. So now oxygen is going to bind to the next one, and it's going to increase the affinity of these subunits. And then we see this cascading effect. And then we get, once oxygen binds to our second subunit, we get an increase in affinity for the third subunit to bind. And here comes oxygen binding even more affinitively to that third subunit, even stronger connection. And so forth, we go to an increase in affinity in the fourth subunit, and oxygen is going to go and increase the affinity to bind oxygen to that fourth subunit. This is called cooperativity. So what happens is these guys are cooperating, cooperativity. They're cooperating with each other to bind more strongly each successive time for each subunit. So that allosteric binding, so in chemistry we call it allosteric binding. The allosteric binding of oxygen is going to increase as the subunits cooperatively work together. So from here now we can make our board a little bit bigger. So put our hemoglobin out into the corner, and we're going to draw ourselves a saturation curve. And we'll call it our oxygen hemoglobin dissociation curve. So now we can start labeling our axes and putting in some numbers. So we're going to put a 0 here. We're going to call this side our percent saturation of hemoglobin. And we're going to call our x-axis our partial pressure of oxygen. And we're going to put it in millimeters of mercury. Now we can start putting some numbers here. Let's mark this as 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, and we're going to go half, to 105. Remember that we said the partial pressure at the lungs is 105 millimeters of mercury. Now we're going to go up our y-axis, and we're going to do the same thing. 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Now, let's draw our sigmoid shape curve. So we're going to start at 105, and we're going to try to maintain this curve, and we're going to come straight down into 0. So let's explain what's going on here. Let's go up to 105, and we're going to drop a dashed line down to 105, and we're going to see that we have 98.5% saturation at the lung. So we're going to change colors, and we're going to do this. And we're going to bracket a couple of regions, and we're going to explain what's going on here. So our first bracketed region is what's going on at the lungs and systemic blood vessels, arteries. Okay, and then this second dashed line is going to be what's happening at a tissue level. Okay, so let's go, and we're going to switch again to red so that we can understand what's going on here. So remember that hemoglobin and oxygen are going to bind. They're going to bind at specific pressures. We could put an analogy. We think about a magnet. Take two magnets and then take the positive end of both magnets and try to push them together. You'll feel that they push apart. So the question is, well, how do you get those two magnets that technically don't want to stick to each other to touch? And the answer is, well, pressure. You can apply a specific amount of pressure to get those ends of those magnets to touch. Oxygen and hemoglobin are no different. Oxygen and hemoglobin technically do not like each other. They're going to repulse each other. But if you apply a specific amount of pressure, specifically here, 105 millimeters of mercury, we will get 98.5% of oxygen binding to hemoglobin. Now, we have a range. So this green range that we just outlined is going to be, so right here, is going to be the saturation at the lungs, and then as it carries to those systemic arteries. And this is good because, look, as we travel down this line, right, and we're in those arteries, the partial pressure is decreasing as we expect it to until we get to the tissues, but the affinity for oxygen, the way that oxygen is binding to hemoglobin isn't changing. We're staying right at about 98.5%, and this is good because this is what we want, and this is what we expect. If you go back to what we just said, we said that oxygen is going to bind 98.5% of it is going to bind at the lung level, right? So we're loading oxygen at the lungs, and then at the tissues we have to get rid of it. We have to unload it. So how do we do it? With pressure. So now we can go back, and I'm going to switch back to my pen marker, and we go back to our tissue level. Now remember, at our tissue level we were at 40 millimeters of mercury, and we follow this all the way up our chart, and we see, sorry, that line's not that straight, and we see that we are about 75%, and that's what we expect, right? So at the tissue, pressure drops to 40 millimeters of mercury, and we follow our chart, and we see that 75% is now bound. So what happened, right? What happened to the oxygen? What happened to the affinity of oxygen for hemoglobin? So now we can say what's happening. We're going to put some numbers to this, and we're going to look at an arterial end and a venous end. So if we look at an arterial end, right, by the time we get to the tissues, we have 98% of hemoglobin is bound, okay? So then what happens? Pressure decreases to 40. We get 75% of oxygen is still bound to hemoglobin. So what happens? So we get a net, so we say 75% of hemoglobin is bound. This is going to be arterial end. This is going to be venous end. So what happened to that 23%? So we do a quick math problem. We subtract 98 from 75, and we see that 23% of that oxygen that was bound to hemoglobin in the arteries was released into the tissues. Okay? Now again, we're naming this as being normal. This is you just sitting still, not really doing anything. This is our normal saturation curve. Okay? So we'll just recap and we say, okay, well, just sitting here doing really much of nothing and everything, temperature and everything being constant, we see that at our lungs it's doing its job. We're loading up oxygen, 98.5%. As we travel through those systemic arteries, we now drop the pressure in the tissues to 40 and percent saturation went to 75. So now, what happened to the affinity for oxygen? As pressure decreases, we went from 105 to 40 millimeters of mercury. The affinity for oxygen went down. Okay, the affinity went down, which means that we started letting up on the pressure on, back to our analogy, the magnet, and they started pushing apart. So again, misconception. People think that we load up 100% of oxygen at the lungs and we deliver 100% at the tissues. This is not the case. We're only losing roughly 23%. Now this curve is dynamic. It changes every second of every day with a few factors. So what we're going to do is we're going to shrink our chart down and we're going to make our whiteboard a little bit bigger, and we're going to look at some factors that affect this normal dissociation curve. Now we're going to talk about things that's going to affect this curve. So we're going to kind of slowly erase some of the things we wrote and introduce some new lines here. Let's see if we could make this a little bit more precise. Okay, now we have our chart back. Let's get our line back. So let's see what affects this curve. So things that can affect this curve, we're going to use this mnemonic. So we're going to shift this curve right and we're going to shift it left. So we'll see what affects the shift right. The mnemonic we're going to use is cadet face right. Okay, so if you think about the military, when you have soldiers in training, they're called cadet, and when they are made to stand in line, they face right. So a right shift curve follows the mnemonic cadet. So we think about things that will start with this letter. So first is going to be C for carbon dioxide. The A is going to stand for acidity. The D is going to stand for 2,3-BPG, so diphosphoglycerate, or 2,3-bisphosphoglycerate. We'll talk about what that is in a second. The E is going to stand for exercise, and the T is going to stand for temperature. Okay, now what happens to a shift right? Let's use a red line to draw a curve shifting right. So we have a right word, shift. Now, what causes that shift right, and we'll make this red arrow here, is going to be an increase in CO2, an increase in acidity, an increase in 2,3-bisphosphoglycerate, which is seen elevated in pregnancy, and this makes sense because those red blood cells are going to be doing more work. And before, when we talked about that byproduct, and we're going to zoom on in right here, we talked about that byproduct that we were going to talk about later of glycolysis. Well, here it is. And the byproduct that we are going to be talking about is 2,3-BPG. Now, we're going to zoom back out and kind of move back over to our shift, and we'll say, okay, well, an increase in exercise and an increase in temperature. And all this makes sense, right? And we'll get into that carbon dioxide, oxygen shifting in a red blood cell, but as you exercise, you become into an oxygen debt, and that you have to repay that oxygen indebtedness. And we know from what we said before that hydrogen ions start popping off as you're moving more CO2. So CO2 increases. Because those hydrogen ions are filling that plasma, that blood, we get an increase of acidity. Because the red blood cells are doing more work, we get an increase in 2,3-BPG. And again, goes with exercise, and our body temperature will increase. So let's look at our saturation, our percent saturation. How does this affect the curve? So we look over here and we say, okay, at a tissue level, and we follow it up, and we say, good, nothing is changing, not at all. So we get 98.5% saturation at the tissue level, and this is good, this is what we want. So we're breathing in and we're binding 98.5. All the oxygen that we could bind to hemoglobin is binding. Where is the change? Let's follow our tissue level up. We go to 40. Big change. We are now getting 50% saturation. So what does that mean? Let's go back to our calculations. And we say, okay, on the arterial end, we are binding 98. We'll make this a little smaller so we have a little more room. We are binding 98%. So at 105 millimeters of mercury through arteries, on our lungs and our systemic arteries, we're 98% bound of hemoglobin bound by oxygen. Now, as we decrease down to 40 millimeters of mercury, what happened? In our venous, so this is again arterial end, in our venous end, we are decreasing to about 50% of saturation. So what happened here? If we do a quick math problem like we did before, 98 minus 50 is 48. So we are getting 48% of that available oxygen delivered to the tissues. And this is smart. So if we zoom back out and go back to things that are causing this, exercise is causing a shift right. Increase in temperature, shift right. On a really hot day when you're sweating, your oxygen saturation curve is going to shift right. Again, dynamic. These are things that are happening all day long. CO2 is increasing. Acidity is also increasing. So what do? We have to repay that oxygen indebtedness. This curve has to be dynamic. We have to be able to adjust the rate of release of oxygen to the tissue. And we did. 48%. We doubled, more than doubled the amount of oxygen being delivered to the tissue with a shift right. So if you think about that in a common sense way, this is what we expect. We're entering into an oxygen debt. The pressure is remaining the same. We cannot change the pressure in our body. But what we can change is how tightly, how strongly, how the affinity for oxygen, to hemoglobin, we could affect that. So by shifting this curve to the right, we decrease the affinity of hemoglobin to oxygen. So while we get to 40 millimeters of mercury, more oxygen is being delivered to our tissues. Now, we're going to take this and we're going to move this out of the way so that we can. So let's go ahead and select this. Move it out of the way. Let's move it down here. And now let's erase what we did so that we have, let's make that circle bigger so that we have more room to write for our shift left. Okay, now let's go back to our pencil. Let's change our color. Now we're going to shift this curve to the left. So let's zoom in. We're going to draw our curve. We follow our same line. And now we shift left. Now, what does this mean? What's happening here? So it's going to be the opposite. CO2 is going to decrease. Acidity is going to decrease. 2,3 DPG is not really a factor here, but exercise will decrease, temperature will decrease. When can this happen? If you are sitting in a lecture room that is extremely cold and your temperature goes down, your oxygen saturation curve is going to shift left. And we'll see what that means at a percent saturation, how that affects percent saturation. Our CO2 is going to go down because we're not exercising. The levels of CO2 is not increasing. Respiratory rate is not increasing, which means acidity is now going to go down because our red blood cells are well oxygenated, okay? And we're at rest, sleeping or sitting still, not really exercising. So let's zoom on into our chart and we'll see how this is affected. Now, again, at our lungs. It's important that all three of these curves aren't being affected by, or all three of these curves, a shift right and a shift left, is not affecting the percent saturation at the lung. We're still staying at about 98.5. The big change is going to be here at the tissue. So let's follow our new line up and bring it across. Now we are at about 85% saturated. So, well, this is weird. What's going on here? So while at rest, while we are, say, shivering inside a classroom that the air is on too high or the heat is not working properly, we could do some math. So let's see what's going on here. At our lungs, we are 98% saturated, right? And again, this is going to be arteries. Now, we look at our new curve, our shift left, we say, well, what happened? On the venous end, we're down to 85% saturated, and this is the venous end. So now we have to do some quick math and say, well, what happened? What happened at a tissue level? We gained 13% oxygen. This is how much was released. 13% of the oxygen was released into the tissues. So the question is now, why? Why did we lose less? Well, less was needed. This is called conservation. We are conserving that oxygen. We took all that time and effort at 105 millimeters of mercury to bind that oxygen to the hemoglobin. Now, when we get to the tissues, we are resting, we're laying down, our body's cold, so we are releasing less oxygen into the tissue. So when can this become problematic? Well, it could become problematic with, say, hypothermia. And this is where people run into big issues. If you submerge yourself into, say, freezing water, if you go back to, say, the Titanic, right, and all those people fell into the ocean and it was freezing cold and they died, you say, well, how did they die? Well, their system shut down, but more importantly, we were delivering less and less oxygen to their tissues, to their organs. Now, here's where it becomes tricky from a nurse perspective. You put a pulse oximeter on a patient's finger, and it will still read 98.5%, although with extreme cold, sometimes when we get vasoconstriction to our digits and our extremities, it will not give an accurate reading anyways, but let's assume that we're getting an accurate reading. This gives the illusion that the body is oxygenating adequately enough. But in reality, we're only giving 13% or less to the tissues, and the tissues can become hypoxic. Now we have one more curve to talk about, and we're going to put this one all the way over here. We're going to make it green. And this curve is going to be fetal hemoglobin. Okay, so this curve is way over here to the left, and we say, what's going on here? So we can add to shift left, so shift left, we can add fetal hemoglobin. So why? What's going on here? Why is there such a shift left? Now, whenever we shift left, whether it be everything in blue here that shift left or fetal hemoglobin shift left, we have to understand that the affinity for oxygen is increasing. And this is important because this is how strongly oxygen is binding and staying stuck to hemoglobin. So we say, why? Why is fetal hemoglobin so different? Well, remember, the baby is not breathing, right? So it doesn't have the ability to oxygenate its blood on its own. So what we essentially make here is a monster magnet, right? A super magnet. So as fetal hemoglobin passes through the placenta, and mom's blood is also passing through the placenta. Remember, they are not mixing. They are intertwined. The blood vessels are intertwined around the placenta. We'll see that this super magnet, this fetal hemoglobin, will physically rip the oxygen off of mom's hemoglobin and suck it onto its own hemoglobin, essentially oxygenating its blood through this leaching or this supermagnet type of effect. So what happens when we see fetal hemoglobin? Well, typically during pregnancy, mom, her curve will be in a constant shift right. As 2,3-DPG is constantly increased, temperature is slightly elevated, etc. So that concludes our oxygen hemoglobin dissociation curve. I hope you found this little tutorial useful.